talking about binomial distribution. Okay, you guys are going to be able to use binomial distribution to solve probability events. Now, binomial distribution, haven't we dealt with something else that's had binomial something in it? Binomial expansion, binomial theorem. This does play a part. Okay, so you are going to see some of that again. You guys remember what binomial expansion was? Binomial theorem, what was it?
No,
you remember?
exclamation mark over.
Where is it the factorial? It's with the triangle.
N minus 1.
Close.
Minus R.
Then there's an R exclamation point. This all came from the combinations N over R type stuff. You guys remember that? And then you would set up the parentheses, and then you had your exponents. You guys remember that?
Yeah.
This is going to come back into play. Okay, it really is. Remember, these two numbers have to what?
Add up to n.
These two have to add up to equal n, and then these two here, they weren't related to each other because we were dealing with like the terms in the expansion. But in this, they are going to relate to each other in some type of way because we are talking about probabilities. So, the essential elements of a binomial distribution are there are a fixed number of trials. Okay, that represents n. N is our fixed number of trials. So we're either rolling this die 3 times, we are either picking out of the bag 2 times, etc., etc. Okay? Each trial has only 2 possible outcomes. You have a success or a failure. You either have, you're picking a 6 or you're not picking a 6. Okay? You're going to have 2 possible outcomes. The probability of a success is constant from trial to trial. So basically, the probability of you drawing a 6 the first time is going to be the same probability that it happens when you draw 6 the second time, and so on and so forth. And lastly, the trials are independent of each other, which means that whatever happens the first time has no effect on it happening the second time. Okay? These are the main elements of a binomial distribution. Now, the outcomes of a binomial experiment and the corresponding probabilities of these outcomes are called a binomial distribution. So basically what you're doing is you're looking at the probabilities and then the likelihood of these probabilities, or the likelihood of these outcomes happening associated with the probabilities. Now the binomial distribution describes the behavior of a discrete variable before the condition applies. The parameters, it's like the requirements that define the unique binomial distribution are the values of n, the number of trials, and p, the probability of a success. Any binomial distribution is represented in this notation, where x represents your discrete variable, b represents letting you know that you're dealing with a binomial distribution, and of course representing your number of trials, and p representing your probability of success. Okay, so again, in that red box, that's the notation for a binomial distribution. Sometimes the problem might be like an actual word problem, so you have to determine whether or not it is a binomial distribution or a normal distribution, which we'll talk about on Wednesday. You'll have that, or you might actually be given that notation, then you have to know that, hey, B represents binomial distribution. So basically you're looking at it like this, okay? You have this event. Something is happening, okay? And then you're going to have these 2 types of outcomes. You're going to have a success, which is basically what the probability of what you're looking for to happen, and then you're going to have failure, which is the probability of it not happening, okay? And then you're basically trying to determine it for a certain number of times, okay? In these cases, tree diagram is out. If you try to create a tree diagram to try to determine the probabilities of something happening, it will take you much longer than what it should, okay? So, let's think about it. Let's look at this particular situation, all right? Let's say you want to determine the probability of getting exactly 2 heads in 6 tosses of a biased coin, for which the probability of getting a head is 2 out of 3, okay? So first off, you're flipping a coin, you have 2 outcomes, right? Heads or tails. However, the probability of getting a head is, you got a weighted coin of some type, so you're going to get 2/3 of the time, which means you're going to get a tail 1/3 of the time. But the thing is, you're also tossing this thing 6 times, which means your tree Have all the essential elements been met? Okay? The essential elements we're talking about, we're back here.
The number of trials.
What's the number of trials for this example? 6. Does it have 2 outcomes? What are the 2 outcomes? Heads or tails. And the probability of success is constant from trial to trial, meaning that what's the probability of getting ahead? 2/3. And it's a biased coin that you're flipping every time, so it's not changing. And yes, just because you get ahead the first time doesn't necessarily mean you're going to get ahead the next time. Is everybody with me? So, all those things are met. Now, what is one possible combination for this probability and its probability? What's one possible combination you can get where you will have exactly 2 heads in 6 tosses?
Head, tail.
So 2 heads the first time and then tails throughout. Okay, so that is one possible combination. Now, how many different combinations are there to get 2 heads and 4 tails?
You can do the thingy though, right?
The thingy, yes. The thingy from when we went over Pascal's triangle, binomial theorem, etc. Okay? We have how many, what's our number of trials?
6.
And how many of heads do we want? 2. So this is 6 choose 2. Okay, there was a calculator way to do it, but real quick, we're going to do this without a calculator to start out with. The formula, Manny and the rest of y'all kind of piece it together, it's what? 6 factorial all over. Remember, what does factorial mean?
6 times 5
So 6, 5, 4, 3, 2, 1. 2 factorial, and then 4 factorial. These cancel out with these because everything's being multiplied. 6 times 5 divided by 2. There are 15 combinations. Okay? There are 15 combinations, 15 different ways that you can get 2 heads and 4 tails. So, I gotta do one part of this. We listed out one possible combination, but we didn't do its probability. So let's go back and do that. Okay? So we have 2 heads. Its probability is 2/3, right? So this is basically 2/3 times 2/3. Is there another way I could rewrite this?
Probably 4 times 1/3 to the 6 out.
Like instead of writing this twice and this 4 times, what if it was like 16 tosses? I'm not going to 2/3 squared.
And 1/3 to the 4th.
Like binomial theorem.
I hate it.
Don't 2 and 4 add up to be 6. What number went in front? What went in front? Y'all remember?
6 now 1. Go 3. 6.
The combination, y'all. The combination.
6. I told you.
Terrible. So basically, this is how you would go about determining this. This is using the process of binomial distribution. 6 combination 2 is 15. What's 2/3 squared?
4 9s.
4 9ths. And what's 1/3 to the 4th power? 1. So now let's multiply this. What is 15 times 4?
16 over 729.
You could have simplified it back here.
Yeah, the 3 make that 5 and turn that 9.
So then you would have had
20 over 242.
But that is how you use binomial distribution to determine that. Okay? All of this, if you did a tree diagram, you would have, God, it would have taken you too long. That's why you use binomial distribution in these types of situations. That, all of this can be simplified down into these formulas right here. If x is binomially distributed, such that the random variable x, such that it's a binomial distribution distribution within trials with P successes. The probability of attaining that many successes out of N trials is the formula N combination R times P to the R times 1 minus P to the N minus R. Basically, binomial theorem. Except this time, your bases are the probabilities and they should add up to equal what number? Take a look at the example. This one we're going to do without our calculator. First of all, without a calculator. Alright, X is binomially distributed with 6 trials and a probability of success equaling to 1/5 at each attempt. What's the probability of getting exactly 4 successes? First off, you already know this is a binomial distribution. N comma P, what's N? And what's P? 1/5. This is the breakdown. So if you're looking for the probability that you get exactly 4 successes, it'd be 6 combination 4. Then you have P, which is 1/5 raised to the 4th power. And then 4/5 to the 2nd power. Because remember, this is P to the R and then Q to the N minus R. So basically your 2 exponents should add up to equal N, and then your 2 probabilities need to add up to equal 1. So 6 combination 4. It is 15. What about this? What is 1/5 to the 4th power?
1/625.
And what is 4/5?
16/25.
I want you to simplify this. I want you to tell me what is the probability of getting 4 successes? So 48 over 3, 1, 2, 5. Yes, remember your shortcuts. Don't sit there and try to actually multiply 625 by 25. See what numbers they have in common. So like 5 goes into 15 and 25 to make this, and this turn into a 3. So then that way at least you're multiplying a smaller number than 25. So make sure you can see later.
125 times 25 goes back to
Yeah.
Alright. Now, 3 or fewer success. What does that mean?
I mean, you have to do the fact.
What would that look like? If I wanted to set up as a probability, it would be what?
6 on the plus and then it'll be factorial.
Oh no, not that part. I mean like this part. What would for
X
B?
is greater than or at least less or equal to 3.
Less than or equal to 3. Which means, if you want the probability of this, that means just the probability of getting 0, 1, 2, and 3, or
the opposite of greater than 3. The complement of anything greater than 3, yeah.
the complement, 1 minus the probability of anything greater than 3, which would be 4, which we just found, 5, or 6.
So much easier.
Okay? It's about the same. It is about the same.
This is
No, actually,
use the
this one you have to do 0, 1, 2, 3. So why don't we just do 5 and 6? And add
This
4.
one I want you to do without a calculator, okay? If you can do this one without the whining and complaining, I will let you use a calculator for the other ones.
It's the same thing, because you have to do 4, 5, and 6.
But you just found 4, so at least you only find 2 more.
And like you stop complaining.
So I want you guys to do this one, okay? It's gonna be set up in a similar fashion as it was with 4. You have to do the probability again of 4, which we just found, probability of 5, and then the probability of 6. Do this one without your calculator. We're gonna do this whole problem without a calculator. After that, we will use our calculator. So, looking back here, I went ahead and redid the probability of it being 4, so that way we can all have the same denominators. So then that way, with all the same denominators, 240 plus 24 plus 1. Did you guys get this one for the purple one?
Yeah.
Okay. So then what would that be when you add them up?
265.
So then you do 1 minus that. So basically, what's 1565? 15,625 minus 265.
15,360.
Divided by 5.
Yeah, 90 divided by 5.
Yeah, it's only 72
Yeah,
You said 30 over
3125.
3,001. How'd you guys get that?
Divided by 5.
Mathematics.
On paper?
Okay.
Yes. You want to see it?
Yeah.
It's not that challenging.
You want to see it?
Can you not long divide
All
it?
right. Remember, this is the only one that we're going to do without a calculator. Now it says at least 1 success. So at least 1 success means the probability of 1, 2, 3, 4, 5, 6, or
It's not 0. Find out what 0 is and subtract.
Or just add
find
it.
out what 0 is and then subtract. So this is the answer to B. This was A. So how do we find probability of 0?
It's going to be 6 over 0, which is 1 over 5 to the same times 1/5 of 0.
1/5 to the 0, and then 4/5 to the
6.
6.
Wow, I hate that.
So what's 6 combination 0?
1.
1. What's 1/5 to 0?
1.
So then what's 4 to the 6 and 5 to the 6?
5 to the 6 is 15,625. 4, 16, 64, 256, 1024. Just write down the board, okay? 4,896. Oh, not
0.96.
Shut up.
So what is 15,625 minus 4096? Thank you for doing that by hand. So here we go. Let's look at this example. It says the probability that I take a bus to work on any morning is 0.4. What is the probability that a working week of 5 days I will take the bus only twice? Okay. Now let's think about it. Tree diagram is definitely out of the question because you got to go Monday, then Tuesday, it's too much. But we can definitely use binomial distribution here, can't we? What's n?
5.
N is 5 because I have a 5-day work week. What's my probability?
0.4.
0.4. And we're looking specifically for the probability that I take the bus only twice. So that's exactly 2. So when we set this up, algebraic, this is what it would be, right? What's the combination?
5, 2, 2.
And then?
0.4. No, to the third.
And then? And it will be 0.6 because the probability that I don't take the bus is the complement of that I do take the bus. Okay? Now we can easily type this into our calculator, yes?
Yeah.
Okay. Remember, the first one's the only one we're doing by hand. This one we'll use our calculator. How do I get 5 combination 2?
Math.
Math 9.
Number.
Nope.
Math 9.
Well, first I have to type the number in first 5. You go to math over to PRB.
It's P.
This one will be C.
This one's C.
What we just went over.
Remember, math over to PRB and then NCR.
You write 2 then?
And then you do 2. So that's 10. So we have 10 times 0.4 raised to the second, and then 0.6 raised to the third.
Oh, that's
268 over 625.
Either one would be acceptable. Well, if you write this one, you can write that or 3 significant figures. So that's the probability. 0.346, or was it 216 over?
Wouldn't you write the exact answer if you could?
That is
If you could, yeah, or 3 significant figures would have been simple. Here's another way to figure this out. Okay? And this one I'm about to show you comes in handy on the ones where like you have to do multiple ones, like the one that we just did with 4, 5, and 6. Alright. What you do is you go to, mind you, we're dealing with binomial distribution. There's a button that deals with distribution. It's located right above your bars button. So you have to press the second button and you go to bars. Second bars takes you to distribution. There's a couple of things in here that we'll deal with a little later. If you scroll down to binomial, you have binomial PDF and binomial CDF. There is a difference between the two. If you want to find one individual thing, like the probability of taking the bus exactly twice, you'll use PDF. But if you were trying to find a range, like say you wanted to find, everything less than or equal to 3, that's like a range, like 0, 1, 2, 3, you would use CDF. Does everybody understand the difference? Okay. So since I'm looking for exactly twice, I'm only going to use PDF. So I click enter. Now, raise your hand if your calculator looks like mine. Okay. Your calculator does not look like mine. Just take a pause for a second. Manny, sit down. Okay? Because I'm going to go over both. Because again, you don't know what calculator you're going to get unless you take yours up there. Okay, but this one's pretty straightforward. How many trials do we have? 5. P represents our success. So it's going to be 0.4. X value. X is exactly how many we want, which was 2. And then basically, paste means it's basically going to paste in exactly what you see. Okay. Now, the ones whose calculator just pops up, binomial PDF, this is exactly what you type in. You type in your number of trials, comma, where's comma located?
Right above 7.
Above the 7. You type in your successes, and then you type in what you want. And then close the parentheses. So basically,
Same thing.
it's going to be the same thing. Like all of our calculators are going to end up looking like this. And when you click enter, same thing.
Where did you get that G6?
When it converts back to a fraction.
Oh, okay.
Called math.
Question. So I suggest you write this down somewhere. Binomial PDF. When you use PDF,
Whenever you're an individual thing.
specific, individual, just one. Okay? So then it's N, comma, P, comma, what you want?
What you want.
Like, like I don't know what's another way.
You can do WIW. What you want. What I want.
That's basically the setup of it. Okay? And it'll get it for you every time. And yes, you could do multiple binomial PDFs all in one line. So say if you wanted to do 0 and 1 and 2 and 3, you could put them all in one line and add them up together. Just put a plus in between each one. You could do
So
that.
you don't have to go to the C then.
So that you won't ever have to use NCR. It does it for you. Okay? Let's look at this one.
You really like it. That's page 1 model.
Okay.
This is a binomial distribution where n is 10 and your probability is 8. If you did treat them as 2 different groups, the setup would have been like so. And they would have had the same, group 1 and group 2 would have had the same setup. But to figure out the probability of all 10 patients were cured in both groups, you would need to do what to these 2 probabilities? You multiply them. So whatever you got, you have to had to multiply it by itself to get 0 point what? is your first non-zero number for your three significant figures? This is going okay for you guys, right? All right.
Wait, it is right.
That's an eight.
Yes.
Kind of wish because I need it for my test.
We got all right. Good job.
Here we go. The last one before we go into expected value and variation. It says the box contains a large number of carnations in which 1/4 are red. The rest are white. Carnations are picked at random from the box. How many flowers must be picked so that the probability that there is at least one red carnation among them is greater than 0.95? Okay? Now, this one's different from the other ones because of what reason?
Didn't give you set amount.
Does not give you your fixed number. So basically, when you look at your binomial distribution, it's n, comma, what? What's the probability of actually getting a red carnation? 1/4. Okay? So we're actually trying to figure out what n could possibly be. Alright? Now we know that we're trying to figure out how many flowers must be picked so that the probability that there's at least one red is greater than 0.95. We know that it has to be greater than 0.95. The question is, what's on the other side? Yeah. What equation? If I know that the probability that at least one red is greater than 0.95, how do I represent that over here?
N over 1 times.
The probability that x is greater than or equal to 1 has to be greater than 0.95, but we have an issue when we use this. What's the issue? At least one of them has to be greater than 9.5. So that means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. What's the issue? Do we know how many are in this box?
No.
So we have to look at the complement, which is what?
3/4. Oh, never mind.
1 minus probability.
What did you say?
Equals 0.
1/4
Okay. Because isn't this the same thing? 1 minus the probability that there are no reds isn't the same thing as probability that there's at least one? Okay. So now let's set this up. This is our equation. 1 minus binomial distribution is going to be what? N over 0. What goes here? 1/4 raised to the, and then raised to the what? N, because again, these two should add up to equal the top number. It's greater than 0.95. Now, don't let anything mess you up. It's like, well, how are we supposed to do n combination of 0?
1.
That's 1.
4 is 1. So 1 minus 3 is 1. So
So
3/4
3/4
to the n. So then you add 1 to that. So you minus subtract 1.
I want you guys to finish this out. This does deal with logs. Should have started out by subtracting. Two negatives when you divide, make a positive.
Did you say anything about that sign flipping? Okay, make sure.
Remember to bring your variable out, you take the log of both sides. And so then, n is what?
10.4, but.
Oh.
10.4, so then that would be 11 flowers that are in there, so then that way the probability of drawing at least one red is 0.95.
Wait, even if.
Alright, well then moving forward, expectation of variance of binomial distribution, expectation before. With the random variables, didn't we just multiply the probabilities by their values? Right? Same type of concept over here, and we're also going to talk about variance. So, expected value and variance of binomial distribution. With the binomial distribution, the expectation of x is n times p. N representing what? Number of trials, and p representing your what? Your probability. So if you have a biased dice thrown 30 times and the number of 6 is seen as 8, what is your probability of getting a 6?
2 over 4 to 15.
It's going to be, how do you get 4 out of 15?
8 out of 30.
Because 8 out of 30 and that reduces. Okay? Now it says the dice has been thrown for a further 12 times. Find the expected number of 6s for these 12 throws. Okay, so what's in? 12. So the expectation is just the product of 12
Yeah, that's what.
and 8 over 30. Okay?
Did you do a proportion? I mean, I guess.
Well,
It's simpler anyway.
So you just multiply that?
Then you just multiply.
12.
12 over 5.
Oh, no.
16 over 5. This could very well be done without a calculator. Something like this would be in a non-calculator section because it is just as simple as multiplying. Expectation. Okay? Now variance. Variance, this is getting closer to the statistics area, is the measure of dispersion, the extent to which the values of a variable differ from a fixed value such as the mean. You guys probably have heard of variance for
Standard deviation.
and standard deviation. Yeah. Like whenever they're talking about, like when they compare you to like everyone else who takes the SAT or the ACT at the same time, there's a variance or there's a standard deviation. Okay? That's basically what they're talking about, basically the spread of the scores. No, it's basically the spread of the scores from the mean.
Wendy's or something?
Alright? So how do you find variance of a binomial distribution? It's very simple. All you do is you do n times p times q, where q is the basically the failures. Okay, the probability of it not being a success. So it's your number of trials times your probability and then times its complement. That's how you find your variance. Something that you probably need to add into your notes is that a lot of times they're not going to ask you for your variance. They're going to ask you for your standard deviation. Because your standard deviation basically lets you know the number in which the spread is of the distribution. So standard deviation, which is represented by this symbol, like a circle with the extra tail, not like theta, but at the top, this is standard deviation. Is basically the square root of variance. Alright? So for this example, when it says in a large company, 40% of the workers travel to work on public transportation, and random sample of 15 workers is selected. Right there, you already know that N is what?
15.
And P is 4 out of 10, or 40%. Find the expected number of workers in this sample that travel to work on public transportation and the standard deviation. Well, expectation is nothing but what? So 15 times 4 out of 10,
6.
which is 6. And then it says to find the standard deviation. Well, in order to find the standard deviation, you got to find the variance. So you remember what it said? It said bar parentheses of x. This is where, you know, those types of questions come into play. So basically all you do is you take 15, you multiply it by 4/10, which we already did, which is 6, and then we're going to multiply it by 6/10. So what's 6 times 6/10? 3.6. To find standard deviation, you do what? Square root it. Use your calculator for this, because clearly, well, no, actually, what's square root of 36?
6.
So then 3.6 would be,
No, but it's not.
no, actually it's not. It's
Yeah.
kidding.
No.
It works that way for 0.36, I think.
Yeah.
Yeah. Not 3.6.
6 over 10 over 10.
1.897.
So reaching figures be 1 point. And there's your standard deviation. So basically from the mean, which is also your expectation. Everyone remember that expectation and mean are the same thing? So basically you have a mean about 6 workers out of the 15 selected are going to take the bus. And then from there, the spread's about 1.9 units on both sides. We're going to talk about this a little bit more on Wednesday when we talk about normal distribution, but it all plays together. Real quick on video, I want to show CDF when you use binomial. Binomial CDF. We're looking at the one that we did by hand, which was this one right here. We're actually going to find B using our calculator because it is a range. It's everything that's less than 3. So this is what you do. You go, of course, to get to your binomials, which is what? Second R's.
B.
This time we're going to go to B, which is CDF. Again, if yours does not show up like mine, that you still set it up in the same type of fashion. Your number of trials was what for this problem? 6. What was your successes? 1/5. So you just do 1 divided by 5. And we were looking for, now this is where CDF can get kind of sticky depending on what is being asked. It always does less than. Does everybody understand that? So in this particular problem, when we're trying to figure out less than 3, that's actually perfect. But if it was to do like 4 or more, you have to do like the complement whenever it's like greater than. Does that make sense? It always does the less than. So your x value is actually going to be.
So it's always less than and equal to?
Or just
Yeah, less than or equal to. Yes. And then we're going to go to paste. So it's set up the same way. When we click enter. Now, what was the fraction that we got for our answer?
3072.
2 over 3125.
Interesting math.
Correct. Math fraction.
Yes.
Oh, okay.
It always says less than.
Less than or equal.
Was that the number we got?
Yeah.
There we go.
Look, we know how to do math.